kept my video. So Dr. Daly is a professor of physics at Penn State, and she got her PhD in physics from Boston University with her thesis on the origin of the diffuse X-ray background and the formation of galaxies and voids. So she's really an expert on the subject she's going to talk to us about today, black holes and galaxies across the universe, which is what you all wanted to hear about. So let's give her some really good active listening, since we've just been learning about active listening, and I'll turn the sharing screen over to her, or Ariana will anyway.
Well, thanks for that introduction. I really appreciate it. Yeah, so I have a PowerPoint presentation. So just let me know when you want me to open that up.
Go for it. It's all yours.
Let's see. I'll minimize this. It's asking me if I want to leave the meeting. No, I don't want to. Wait a minute. Let me see. Are you seeing my PowerPoint?
No, there's a little green button at the bottom that says share.
All right, let me. Let's
If you
see.
need to send it over to me at the last minute, I'm happy to
Okay, screenshot. I've got it.
Okay.
it. Sorry. It's been a while since I did this remotely. Let's see. So
There
are
we
you
go.
seeing?
Okay, yeah, that's good.
All right. So let me try to remove all of the icons here. Let's see.
Oh, we're not. It's looks okay to me.
Right. I can only part of the, well, all right, part of the screen is not showing up for me, but that's all right. I'll make do. That's fine. All right. And I was going to say if people did want to interrupt me while I'm speaking, that would be okay with me. Or you can save your questions till the end. So I would like to figure out, let me just see this, about a third of my screen is currently covered with, let's see.
Maybe the chat or the participant list or something. You can just close those down. There's like a little X in the top right corner of each one of those.
Okay. Well, I'm just gonna, I'm not seeing that. I'm just gonna move forward. So in this screen, I have 3 examples of black holes. So the first example here in the lower left is showing a star, what we call a stellar mass black hole. That means it's a black hole that has a mass like the mass of a star, maybe around 10 times the mass of our sun. And it's getting some material from a companion star and it's shooting out these jets. So one of the themes with black holes is that we don't detect the black hole directly, normally. We see these black holes because they have material around them, or they're in a binary black hole system, and we see a star moving around something, but we're not seeing any light from that something. Okay, so this is a stellar mass black hole that's got a companion star that's providing this gas, and the gas lights up and allows us to detect the black hole. The similar thing can happen in a galaxy. So this middle slide would indicate a black hole that has a mass like the mass of 1,000,000 solar masses or 1,000,000,000 solar masses, where one solar mass is the mass of our sun. And sometimes these black holes put out these tremendous jets. So in the lower right here, we have a very massive black hole, about 1,000,000,000 times the mass of the sun, way down in the center here. And it's putting out some very, very powerful jets. All right. So let me just, I'm just going to see if I can clean up this screen a little bit. Oh, good. Okay, I'm getting that down here. Minimize it. Okay, great. This is a lot better. So now let's talk about some things we can see from Earth. We can see stars like our sun. Here's our sun over here on the left. We can see galaxies. So here is a spiral galaxy like M31, our neighboring galaxy, the Andromeda galaxy. We have elliptical galaxies, which are old and pretty round in shape, spherical in shape. And then we have some galaxies that are active, where the black hole at the center of the galaxy has material swirling around it or is producing jets. Now, each of these objects is held together by gravity. And we see them because they're emitting light at some wavelengths. Sometimes we can detect black holes through gravitational waves, and I'll mention that later. But right now we're interested in objects, masses held together by gravity that emit light. Now, we can detect black holes by measuring the effects of a strong gravitational field. So we've detected both black holes that have masses like the masses of stars and masses like the masses of small galaxies, so 1,000,000 to 1,000,000,000 times the mass of our sun. So the first thing we have to understand is how gravity works when we're studying these. So stars are held together by gravity and they emit light. And stars might put out more light in the red area of the spectrum. They appear kind of red, and some put out light in the blue area of the spectrum that we see with our eyes. And but they're held together by gravity and they emit light. Now, you might be familiar with the Big Dipper and something called the Hubble Deep Field, which was observed with the Hubble Space Telescope, focused on a very small region of the sky that's near the Big Dipper. And if we blow that up, they studied stars and galaxies in that region and then focused in on a little tiny patch of that sky. And when you blow it up, you get this. So this is the Hubble Deep Field. And every little smudge in here that we see is a galaxy. Some are nearby and some are very, very far away. Things with these sort of diamond-shaped pattern here, which we call diffraction spikes, those are things that are point-like and are probably stars within our own Milky Way galaxy. And we're sort of seeing through our galaxy out to the universe. But every single one of these other things is a galaxy, sort of like the Milky Way galaxy, and it's held together by gravity, and it emits light. Now, how does gravity work? Gravity is really the warping of space-time caused by the mass of a body. So, for example, this is the Earth, and the Earth is affecting the space-time around it. So, if we imagine that before the Earth was here, this was a perfect grid, kind of like graphing paper, a nice grid, totally smooth in every point like every other point. And then when we place the Earth in it, it pulls in the grid. And now when things orbit around the Earth, they're really moving in straight lines in this curved space-time. So this is our current theory of gravity. It's called general relativity. It was proposed by Einstein in 1916. And so far, all of the predictions of that theory, which are extensive, have been confirmed with experiments and observations. So far, we haven't had anything observed that is not consistent with this picture of general relativity. So it says that what's happening is a mass is actually deforming the space or space-time around it. And that is what we refer to as gravity. So here is another picture of a mass distorting the space-time around it. And this might be a planet moving around something like the sun. So as far as the planet is concerned, it's actually moving in a straight line. It's just that all the lines are in some sense warped or curved by the presence of this mass. Now, when we have something like the sun, which is not a black hole, there's a fine, we can see the surface of the sun, and things could go, a light ray could go right through the sun and out the other side, and it would not be swallowed by the presence of the sun. Now, as the mass gets more and more compact, denser and denser, so if we took the sun and we squished it down and made it smaller, as we make it smaller, the sort of the indentation of the space-time around it becomes stronger and stronger until finally, if we took the sun and squished it down so that it was just a few miles across, these lines would go just down into what we call a black hole. So that if we put some light, if we shone some light in toward this region, it would never return. It would not come back out the other side. So that is how we define a black hole. Now, very quick history. So Albert Einstein predicted this theory, came up with this theory over 100 years ago. It was a mathematical description, and then there was something called solutions, which Carl Schwarzschild came up with, the vacuum equations and the solutions. And one of them was for a black hole and then a rotating black hole. So I'm going to be talking about not just a black hole where no light can come back out once you shine it in, but then we also can have rotating black holes. Now, I wanted to mention John Wheeler because I got to know John Wheeler quite well when we overlapped at Princeton. And in fact, he gave me his desk, which I'm sitting at right now to give you this talk. Let's see. Other important names are Roger Penrose, who talked about the Penrose process and proposed the Penrose process, where we can remove energy from a spinning black hole. So I'm going to talk about that. And then the first identification of an actual black hole happened in 1972 with a stellar mass black hole around 10 times the mass of our sun called Cygnus X1 was detected. Oh, and here's John Wheeler and his wife Jeanette at my home when I was in Princeton. But you may be familiar with the constellation Cygnus the Swan. And the next time you look at that, you can imagine that there is this black hole in this lower part of Cygnus the Swan called Cygnus X1, the first X-ray source detected in Cygnus, and it was later determined to be a black hole. So what's happening here is this little dot in the middle would represent the black hole, and it's in a binary star system. So before this star turned into a black hole, we had two stars orbiting each other, gravitationally bound, and then one of them blew up and left behind a black hole as a remnant, and now that black hole is dragging over material from its companion star, and this material around the black hole is very, very hot, and it emits X-rays. And the current estimate for the mass of this black hole is around 21 times the mass of our sun. And it's a bright X-ray source, so it's called Cygnus X1, the first X-ray source detected in Cygnus. Now, when you have binary stars, okay, so here are two stars, and they're held together by gravity, and they're orbiting one around the other. Now, if one of these ends its main sequence lifetime and explodes, it can leave behind a black hole. So if you then come back and observe this after that event, you would see one star, say this star here, moving back and forth, but you would not see this other star here. These stars might not be close enough to have that mass exchange that led to the X-ray emission in Cygnus X1. So one way that we detect what we call stellar mass black holes of a mass like a star, like 10 solar masses or 20 times the mass of the sun or 30 times the mass of the sun, sometimes we see something like this, one star moving back and forth, and we can figure out how massive the unseen companion must be to have that orbit, the one that we see, and then we can figure out, well, if it's massive enough, it's got to be a black hole. So that's one way we detect them. Now, this slide goes back a little over 10 years, but these were the 21 known black holes in our galaxy, the Milky Way, and in some of our local galaxies, the Large Magellanic Cloud and a galaxy called Messier 33, there were 21 detected and identified black hole systems because you could see one star moving back and forth, or you could detect the X-ray emission from the transfer of mass from one star to the other. So there's not lots and lots known, but there are certainly plenty known where we figure the companion has to be a black hole. All right. So in addition to looking at stars, we can look at galaxies and the center of galaxies. And you've probably heard about the Event Horizon Telescope. I'll tell you a little bit more about that later, where we look right at the center of our own galaxy, the Milky Way, at the center, which is called Sagittarius A star. And we can look at the center of a nearby cluster of galaxies. And at the center of that cluster is a giant galaxy called Messier 87. And at the center of that, there's something called Messier or M87 star, the star indicating the presence of a black hole because it's so small. So the little star means that it's really small. So I'll talk about that in a little bit, but now we're coming up to modern times. And in modern times, we have detected black holes indirectly through the gravitational waves produced when two black holes coalesce. So I'll mention that in a little bit. All right. So the center of our own galaxy, there's a constellation. It's in the constellation Sagittarius, and it was named Sagittarius A star because there's something that is point-like there, like a star, but it's very, very massive, like around 4 million times the mass of our sun, and it does not emit any light. But what we can do is look at the motion of stars going around the galactic center. And there are two key groups that have done this, and now other groups are expanding on that work. So by looking at the orbits of stars around the galactic center, you can figure out how much mass you would need to keep these stars on the orbits. So these orbits are they're really moving around a space-time where the whole space is sort of like a trampoline with a big dent in the middle, with that big dent produced by this big black hole, 4 million times the mass of the sun, sitting at what we identify as the center of our galaxy, and it has a mass of around 4 million times the mass of our sun. And for scale, the distance between the sun and the Earth is 1 astronomical unit, and this length here is around 1,600 astronomical units. So these are small, very, very small scales. in the scheme of the center of the galaxy. All right. All right. So let's continue on. Now, we also have something like Messier 87 at the center of the Virgo cluster of galaxies. If you zoom way, 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 way in and study that source, what you see is that it has this very powerful and very thin, I call them cigars, that is emanating from the very central region of the active galaxy. So the active galaxy at the center here would be identified because it's a powerful X-ray emitter and emits light that is different from the light emitted by stars. And then it has this very, very powerful jet. So these are called active galactic nuclei, or AGN, sometimes referred to as quasars. We can study these to figure out the mass that is at the center here, sort of causing that big indentation of the space-time around it. And at the center of every galaxy, there's a lot of evidence that there is a black hole at the center of every galaxy. And when that is active, so there's a lot of hot gas around it, for example, producing X-rays, or we see these highly collimated jets, these big cigars coming out from the central region, we're pretty sure that those are produced by processes associated with a very massive black hole at the center of the galaxy. And these can range from a few million solar masses, like the one at the center of our galaxy, to several billion times the mass of the sun. So a very broad range of black hole masses, usually associated with the size of the galaxy surrounding the black hole. Now, we think the active phase is short-lived. So galaxies that are not currently active, where they don't show up as having properties that we can't explain by stars, once that turns off and is done, those black holes will remain at the centers of those galaxies. Now, I've gone back to the Hubble field. This is the Hubble Ultra Deep Field, which we talked about earlier. And we see there are elliptical galaxies in the field, which are sort of like giant balls. They're what we call spherically symmetric. And then we have spiral galaxies, which for the light in the spiral galaxy is collapsed down into a plane, and that's what the Milky Way galaxy looks like, we think. And there's also irregular galaxies, which have other shapes. So we think that at the center of every single galaxy, there's a black hole. And in this picture, the only thing that's not a galaxy is this object here, which is a foreground star. We can tell from these diffraction spikes. That means this is not resolved by the Hubble Space Telescope. Here's another one up here. So except for these two things with these sort of star-like features, everything else here is a galaxy. And we think every single one of those galaxies has a big black hole at its center, and probably lots and lots of stellar mass black holes throughout each galaxy. Now, if a black hole is spinning, well, let me start again. If a black hole is not spinning, it would be spherically symmetric, like this red picture here. And it would be pulling in the space-time the same way in all directions. So if it wasn't spinning, it doesn't have a preferred direction. Now, if the black hole is spinning, and there are several ways to spin up a black hole, one way is if the material falling onto the black hole carries angular momentum, so gas is swirling around and falls into the black hole, it's going to spin up the black hole. Or if you have two black holes come together and by gravity coalesce, the black hole that forms is going to be spinning. And a spinning black hole does have a preferred axis, and it has a region called an ergosphere. And so the way it affects the space-time around it is a little different, and it's stronger in one direction than it is in another direction. So what Penrose showed in the 1960s is that the energy associated with the ergosphere can be extracted, which means that some of the spin energy of the black hole can be removed from the ergosphere. And that's something that I am working on now and have been working on for several years. Well, let's think about a spinning black hole. For example, M87 star, the black hole at the center of M87 in the Virgo cluster. It has a mass of around 10 to the 9 solar masses, around 1 billion times the mass of our sun. And it seems to be maximally rotating, which I figured out, and other people have similar results. And I'll mention that in a little bit. We think it's maximally spinning. Now, what would that look like? Well, a 10 to the 9, 1 billion solar mass black hole that's spinning as fast as a black hole can spin would rotate about once per day. So that would be sort of a region within the ergosphere, would go around once per day. But how large would that orbit be? It would be around the size of Saturn's orbit around the sun, or around 10 astronomical units in radius. So the Saturn actually takes around 30 years to go around the sun once, and a maximally spinning billion solar mass black hole would be about the size of Saturn's orbit, but it would spin once in one day. Now, if you look at the relativistic jets that are coming out from M87, and there's some beautiful jets, and they're primarily observed in the radio range of the electromagnetic spectrum, the power coming through that is around 10 to 100 times greater than the entire output of the Milky Way galaxy. So these are fascinating objects to study, putting out tremendous amounts of energy in a very, very small region. And, they have some very, very interesting dynamics. So we'll go on. All right. So you probably have heard about the Event Horizon Telescope. And this is a real tour de force of engineering and great ideas. And they have been able to focus in on M87, the very, very central region of the black hole at the center of MESS 87. And here is a little circle showing something about the size of the solar system, so about the size of the orbit of Saturn. And they're able to see emission coming from the region around the black hole. Now, the light we see is distorted and amplified, and there's a lot of effects because it's coming from that region where space-time is sort of warped, like putting a bowling ball on a trampoline, and also because it's probably rapidly spinning. I think it's maximally spinning, and there are other observations and other techniques to measure black hole spin that come up with similar results. So, but in any case, this is really fantastic to see down to this scale and see what we call the shadow of the black hole. So this would be a side view. Here are those jets, or an artist's impression of what those jets might look like. And they might, the axis of the outflow is, I would say, almost certainly related to the spin axis of the black hole, and may actually be produced by taking the spin energy of the black hole and channeling it into these relativistic outflows. So this shows some of the telescopes that are used to put the Event Horizon Telescope together. So all of these telescopes all over the world work together and collect data, and then they try to bring all that data together to put together the image that I was showing you a few minutes ago. So this is what M87 would look like in an old catalog of galaxies. So we're looking right at the center of the Virgo cluster of galaxies. It's a cluster, that means a cluster of galaxies is held together by gravity. There's about 1,000 galaxies in that cluster of galaxies. M87 sits at the center of this giant thing and has probably gobbled up lots of galaxies in the past. So it's what we sometimes call a first-rank giant elliptical galaxy. It's an unusual galaxy. And this is the active nucleus zooming down, and you can see it in the X-ray very clearly. You can see it in the radio range. You have to look through all of the stars, gas, and dust. So sometimes it's best to look outside the visible range of the spectrum. And then this radio jet, which also shows up in the X-ray, is, very prominent and easy to see. And that black hole at the center of M87 is around 6.6 billion times the mass of the sun. That means it's 1,000 times, or really around 15,000 times, as massive as the black hole at the center of the Milky Way galaxy, which is only 4 million solar masses. This is 6.6 billion solar masses. A fabulous and wonderful, interesting black hole to study. So these are the Event Horizon Telescope images of M87 in what we call continuum. So sort of a bunch of different wavelengths. We look at several different wavelengths at once. And then this is in polarized light. So we're just letting through light that has one particular polarization. And what that means is we can see the magnetic field structure. So this gas or plasma, which would be, electrons and protons, or positrons and electrons, that is emitting light right around the very heart of the, right just outside the ergosphere of this black hole. When we look at it here, this indicates that there are very strong magnetic fields in this plasma. And that is a hint that the extraction of the rotational energy of this black hole could very well be producing the jetted outflows from these sources, and in particular this source. And also in Sagittarius A star, it's recently been reported that a very similar polarization pattern is detected by the Event Horizon Telescope group. And this fits in very nicely with work done by many, many people on the role of black hole spin in producing jets. And if I have time, I'll just tell you a little bit about the work that I have done on that
Oh, we're sort of running out of time, unfortunately.
Oh, okay. Here's Sagittarius A star and polarized light. Okay, I'll wrap it up then. Just to give you a taste of what I'm doing something called the outflow method, where I use the properties of the outflow and the properties of the accretion disk plus the black hole mass to solve for the black hole spin and figure out how rapidly these black holes are spinning. And I found that both M87 and Sag A star are rapidly spinning. And these are our results on Sag A star. They probably don't mean a lot to you, but this thing here, A star, this is the spin value of of Sagittarius A star. If this was 1, that would be the fastest it could possibly spin. So it's at around 90% in terms of its spin. So black holes are really cool. There's a supermassive black hole at the center of every galaxy. There's numerous stellar mass black holes throughout each galaxy. And sometimes the black holes at the center of galaxies produce these wonderful jets. So I'll stop there and see if there are any questions.
Thank you. Let's give a round of applause for our speaker. And if you're in the chat and you couldn't tell, black holes are also Lynn's specialty area. So she's been fielding a bunch of questions in the chat.
Oh, yeah, I couldn't pay attention to that during
Yeah,
this. So,
that's perfectly fine.
thanks
Um,
for fielding the questions.
That was a wonderful presentation. Thank you very much. But we
My
do have,
pleasure.
we
We
do
do
have
have,
a question from Sid that I didn't answer yet. So we could do that one.
yeah, Sid asked, so does the telescope use the radio jets to photograph the black hole?
No, they don't. What did someone else want to say something?
I just said not exactly. I'll let
Not
you explain.
exactly. Yes. No, the Event Horizon Telescope, are they asking about the Event Horizon Telescope?
Yes.
Okay. The Event Horizon Telescope, which is a combination of all these telescopes all over the Earth put together sort of electronically, they're really focusing right in on the heart of M87 and Sagittarius A star. And with the radio, I think the closest we can get in is probably at least, do you know, Lynn, like 10 to 50 times larger in scale than the Event Horizon Telescope?
Yeah, the Event Horizon Telescope was able to, make this image, which is about a millionth. The resolution is about 1 million times better than the Hubble Space Telescope, because Hubble can't resolve anything like that. Hubble's a factor of 1 million away from being able to make a picture like that.
Right, right. The radio is though VLBI. So that's the VLBI, the radio images are not able to get down to this level, but I think they're probably within a factor of 10 to 100 of that scale. But then they just see the radio emission.
Right, so they need to add up the signals from all the different telescopes in the Event Horizon Telescope to make the images that have been published.
Absolutely.
So then Hubble has a resolution of about 1/10 of an arc second. So these are about a 10th of a millionth of an arc second. So
Yeah, right.
1/10 of an arc second kind of images that after you add up all of the different telescopes. And the only way you can do better is to have a longer baseline between pairs of telescopes. And so people have been talking about putting one on the moon so they could actually have a really long baseline. Yeah, so aperture synthesis basically allows you to mathematically add up the signals from all the different telescopes. And make
Exactly.
and so then it acts like a telescope that's as big as like half the Earth.
Right, right. Yes, that's right. And in the radio, it's a similar thing with VLBI, very long baseline radio interferometry, but you don't see the type of emission that they see here. You can't image the black hole the way that they're able to do at millimeter wavelengths. So yeah, I agree with everything you said.
Anyway, it's pretty cool. The Event Horizon Telescope was quite the breakthrough because even looking at these two really big, or well, one's really big and one's not as big, but it's a lot closer. Black holes is they probably not a whole lot more of them they can actually use their technique on to make images. Although
Right.
I'm sure they'll try. But I had not seen the polarized ones before, and it's just so cool to see the magnetic field lines like that. That's just fascinating.
Well, the polarized ones are really, really amazing. And if I could just give a little plug for my work, I actually the work found I have this method called the outflow method, which gives magnetic field strengths. And people have been saying your field strengths are way too high, but guess what? They're coming right in, very similar to the values. This was unexpected. This very strong polarization, especially around Sagittarius A star, but also around M87. That was not expected. So there's surprises, and we're learning a lot. And it's going to, this may be telling us about how rapidly these black holes are spinning. Because it kind of drags the field lines around and stretches them out and amplifies the field.
Right.
Are there
Final
any
questions?
Do we have any budding astronomers in the crowd?
Oh, yes, definitely.
Oh, good.
They requested this talk subject, so that's why we asked you, but it's so that was a really excellent talk. Thank you so much.
Of course, it's my pleasure. It was nice to see you all, and best wishes for your future in astronomy. So I guess I should sign off now.
Yep, if
Yeah,
the students can stay on, we have our 4-question evaluation survey just before we wrap up. But we can give a final thank you to Dr. Daly.
Okay, and great to see you, Lynn. Thanks for inviting me. I really enjoyed it.
hopefully we'll see each other in person again someday soon.
I know. Well, I'm going to be in Miami in December. You're always welcome at the meeting.
Oh, the Cartwright meeting. Yeah, I was thinking about
Yes,
it. Okay, we'll
I
think
can
about
send
it some more.
I can send you a link on that. I'll do that
Yeah,
tomorrow.
no, they sent me, they invited me. I just hadn't decided if I could go or not yet.
Yeah, okay.
Ruth, is it okay with you if we post this talk on our N3 website?
Sure, that's fine.
Okay, well, thank you so much.
All right, see you later. Bye.